I'm always stop in the middle. Well, we can just announce that everybody who wants to go can go now.
Our next speaker is Eyal Markman, who will give a talk on Morrison-Kawamata conjecture.
Thank you very much for the invitation to speak here. Pleasure. And thank you for staying so late. So this is joint work with Kota Yoshioka, and it's I think a fundamental story. So which relies on the work of many people. So my contribution is very partial, and I'll talk about results of many other people. All right, so this is Morrison-Kawamata. Conjecture. And so there are a lot of codes, so let me define a few codes. So let X be an irreducible holomorphic symplectic manifolds. This is almost so one before last, so I don't think I need to define it. But for example, X could be a K-free surface, or the Hilbert scheme of endpoints on a K-free surface, or the formation of the Hilbert scheme. And so now, so set lambda, this is a lattice. So this is the Picard lattice of X. So or the Picard. So this would be our lattice, and and it has signature 1 or minus 1. Or is the Picard number, the rank of the Picard, and of course it varies with the complex structure. It jumps, and for generic X, which it may not be algebraic. So this is if X is projective, and for the main result we need this assumption. I should say that most of the results here were generalized and not both generalized and proved independently by Amerik and Verbitsky. So for generalized in the sense that they prove it for any Kahler independently from us. All right, so okay, so this is the first, and now we have this is the lattice, and then we have the vector space corresponding to it. So this is just a tensor with R, and inside it we have the positive code. So this is the connected component. So let's assume that X is projective. Connected component of the following of cone, which is lambda in lambda R, such that the self-intersection is positive. This is with respect to the Beauville-Bogomolov-Fujiki form. So if X is a K3, this would be the intersection pairing. Otherwise, X comes on with a form on H2, and in particular on here, the signature that I wrote here is with respect to this Beauville-Bogomolov-Fujiki code. So this is the connected component containing the Kahler class, containing the Kahler code, the ample code. We are working with algebraic practice. What else do we need? Okay, so we have the ample cone will be the ample cone. And then we have the Neff cone. This is just the closure of the ample cone in the vector space. And we have the dual now here. This is slightly non-standard. We have the dual cone to the Neff cone, but we'll think about it as a cone in the same vector space, because this comes with a pairing. This is the dual cone. So these are classes here, intersect classes, Neff classes with non-negative intersection. And then we have the following definition. And I'll relate it soon to the Morrison code. So this is related to, maybe I'll say it now. We have, let's see. So we have this sits in H2 XR, which is isomorphic to its dual by the pairing, which is isomorphic to H lower 2, the homology. And inside here, so inside here we have Neff, the dual, and inside here we have the Kerr classes, the Morrison, it's closed cone, Morrison. So this is the closure of the cone generated by effective one cycles, effective curves. And it is well known that the Morrison is dual to the Neff cone, and so this just by definition and spec, we have this relation. So extremal, I'm going to define extremal classes here. This will correspond to extremal rays in a Morrison. Okay, so definition. A class non-zero class. Class lambda in is extremal. This would be invariant under the scaling if any decomposition lambda equal lambda 1 plus lambda 2 lambda I in the dual from this version of the Morrison consists of, so any decomposition with these classes in the cone consists of lambda i's, which are scalar multiple of lambda. So you cannot essentially decompose. Okay, so yes, questions? So now we have the basic conjecture. So I'll call it the boundedness conjecture. And this conjecture is known, I'll say where. So, the set, following set, so these are a set of numbers of self-intersection with respect to the Beauville-Bogomolov-Fujiki pairing, where E is here in the Morricon essentially, is an integral primitive, so it's indivisible, and extremal. I think that's all I need. Yes. So this set of intersection numbers of extremal classes is bounded below by a constant, I don't know, I'll call it n, and I'll put bracket x, which depends only. That means if you work, I'm going to say that it depends only on the birational class of x. So if you have a birational model which is also holomorphic symplectic of x, let's say y, then when you take the same analogous set here, it will be bounded by the same constant. And I'm not saying that they have the same bound, but there is if you run over this union over all birational models, then it's still bounded, which depends only. So I said it not in a good way. So I should. Anyway, it depends only on the birational cluster.
Wouldn't it be true deformation equivalence?
Yes, but it's a stronger conjecture. So I just wrote the weakest one, which is sufficient.
I think the stronger is just.
Yes. Oh, you prove it?
Well,
you're about to prove it.
I'm not quite sure. Probably not.
Okay, so it's almost proven. This conjecture is almost proven by Verbitsky and Amerik. They are working on it. Hopefully, it will be proven. Let me just say that here I mean that the union of these classes of the all birational model is bounded.
And it is clear that all extremal rays are rational.
Rational.
It's
yes.
Known.
Yes, that's
clear, but it is known.
Yes.
Well,
You can find it in, I mean, it follows from birational geometry, and it's written explicitly by Hassett-Tschinkel in 2019.
But it depends on what you call extremal ray, right?
Well,
because I mean,
that's what I call
the cone can be circled in some way.
Yes.
so the question
Yes.
was
Yes. Okay.
If you have a circular cone, then every ray is extremal and.
No, I know. They're integral. They're extreme. All right. So we have the conjecture. Oh, so let me just say example. If x is a K3, actually, one always have to think about K3s first, because there are many statements which are not given here. It's clear. If x is a K3, then the set of constants here are 0 and -2. So these are which is bounded from below by -2. Okay, so extreme irrational curves on the K3 are -2 curves, and you also have elliptic fibrations, and that's it. So, and now let me say what happens when X is a Hilbert scheme of. So the conjecture is known. For moduli spaces, for projective smooth moduli spaces, M V of stable H stable. She is a more general stable object. She's actually on a K3. S. This is by Bayer and Macri. And for any, so this is a more general, for any X deformation equivalent to Sn by using Bayer-Macri by Bayer, Hassett, and Tschinkel. Now, and also by Mongardi, and also by Amerik and Verbitsky. I think these are all even. Okay, so all right. So I want to say that so if so let's get. I just want to state the ample cone, the description of the ample cone due to Bayer and Macri. So X is a moduli space of sheaves on a K3 S, which is polarized with an ample class H. And all right, so in that case, we have the Mukai lattice of S. And this is isomorphic to, this is the whole cohomology, but the pairing plus the Mukai pairing. And I don't want to get into its definition, but it's the intersection pairing on S derives the rank 2 unimodular hyperbolic lattice. So this is with intersection matrix. This intersection matrix. And now using so we have the universal sheaf or possibly twisted, which is okay, or quasi over S cross MB.
So you mean H star of X Z is H?
Yeah.
Okay, sorry.
Okay. So and then now here's the story. So V, I didn't say what V is, but above the V that appear in the notation above, V is the Chern class of sheaves in MHV times square root of the third class of S, and it's an element of this Mukai lattice. And then using if you take the Chern class of E normalized with some third classes, and you regard it as a correspondence, then you get H2, a description of H2 of the moduli space. And this is isomorphic. Now, I think the direction is confusing. Yes, so I want to choose so this is isomorphic. I'll call this theta to V pair. Actually, theta is the inverse of the Mukai map. The natural map goes for, and this V pair is with respect to the Mukai pairing. It's containing H star SZ. Right, so there is a map. So the Chern character of E essentially gives you a map from here to here, which restricts to V pair as an isomorphism, and we invert it and call it theta. And so this is an isomorphism. It's Mukai isomorphism. This was proven by many people that it's an isomorphism, including Beauville for Verbitsky, Mukai, Hulbert, Grady did a lot of work, and Yoshioka got the final answer for any moduli space. And okay, so now what I want is to take the adjoint of theta. So this is isomorphic to H, which is we need for the description. So we have the dual space, and we have the dual of this.
So do you assume that the moduli space is more than 2 dimensions?
Yeah. Thank you. And everything is known in the case of the K3. So assume that we got, and if Mukai proved that if this modularized space is two-dimensional, then it is a K3. We know the ample cone. So assume that the dimension is bigger than 2. But only in that case this is true. Otherwise, you need to mod up by the class of it. Anyway, so we have the dual, but these are isomorphic via the Mukai pairing. This is a unimodular lattice, and this is actually only contained as a lattice. And so we have the adjoint. This is the adjoint map, and let me call this theta V for the composition. So we have a map of the Mukai lattice. And this we think about as H lowercase 2. So we have this map just defined from the Mukai lattice to H lowercase 2. And now I'm going to describe Bayer-Macri's result about the ample cone of the next cone. So theorem. Bayer-Macri. So we need to choose an ample class. So let H be an ample class on the moduli. And so the Morricone of MHB is generated by the following set. By the image via maybe I want to say something just a second. If we can think about this, you see, once you tensor over Q, these are actually identifications. So we can think about this sitting in the rational vector space spanned by this. And under this map, this phi dual, this is just a projection.
Sorry,
yes.
Dimension, right?
Say it again, please.
Left hand side is 23 dimension. And right hand side is 24.
24, yes.
And left is 23.
Right.
Yeah, but it's orthogonal.
Huh?
It's orthogonal.
No, the orthogonal is isomorphic. This is contained.
They are from
The isomorphism is above.
Your diagram.
And now I'm saying this is just projection onto this conic one sublattice. That's okay. Question?
Is your diagram computed?
Yes.
And you see that the left vertical map is an isomorphism of the tensor in the Q.
Yeah.
But it vectors.
All right. So what is the ample cone? Is the image via this projection. So this is just projection. Maybe I should have done it. This is just projection onto here. That's what all it is. Orthogonal projection. When it tensor of Q, of course. All right. So it's the image via of the set. So these are A in. So you see, it's kind of funny. You want the description only in terms of the H2, but the description of the net cone depends on an embedding of H2, the second cohomology, into the Mukai lattice, which has rank 1 bigger. This is crucial. So it's A in the Mukai lattice. Such that Okay, so here, so AA is bigger than or equal to -2. This is related to the bound in the conjecture. It's bounded below. And also, if you pair A with B and take the absolute value, it's less than or equal half the self-intersection of B. This is half the dimension of the modular space -1. And let's see, there is one, and the ample class. And if you take H, so this is a generator of the Morricone. The Morricone, yes. And this is paired with an ample class. Ample class evaluated, and this should be positive. No? Right. So this is the generators. And so this is a boundedness statement, and this boundedness is needed in order to bound the projection. It's combining, it's an elementary linear algebra that if you combine these two inequalities, it follows that the projections are bounded. Okay, so the conjecture follows. Conjecture follows. And you'll have a description of the ample form, which is pretty amazing, I think. It's a very hard thing to compute. All right. Questions up to now? All right.
So the last inequality is straight.
Is what?
The last inequality is
Straight. Yes. You want non-zero classes, which are. All right. So okay. So now I want to state the main result.
So the last line is just the intersection of H and.
Yes, except that I'm thinking about H as a cohomology class, and this is a homology class. So that's why I need that.
There's a pairing.
Yeah, but if you are thinking about the homology sitting in the cohomology, then it's the intersection. Yeah. Okay, so now definition. So let's see. How many cones do we have? Maybe I should have up to now we don't have. We have the ample, the F. Everybody knows them, and we have the positive cone, and that's it. So here's another one. Let Nef X plus. So what is it? So let me just say that we are going to. This is not closed and not open. We are going to add to the ample cone just rational rays of the boundary. So we have, I'll just say it first. So this is the convex hull in our vector space. Remember, this is the Picard lattice, essentially the algebraic part of H2. Convex hull you take the Nef cone, this is closed, and you intersect it with all the rational points, rational vector space in this vector space. So this is what we need. It's a kind of a funny construction, but I'll explain it. So since this is dense and the ample is the interior, certainly this contains the ample cone. And it's contained in the Nef cone, which is closed. But so what is the difference? So Nef plus X minus the ample cone consists of R plus times lambda, where lambda is a rational Nef isotropic classes. That's what we add. And okay, so now why do we do this? Because we want to fit inside. We want to say that essentially the ample cone. I'm about to state the Kawamata-Morrison conjecture, which is a theorem conditional on the boundedness conjecture. So we want to say that we want to find a fundamental domain for the action of the automorphism group on the ample cone. But we want the fundamental domain to be closed. And the ample cone is an open cone. So we add the minimum we need in order to find a fundamental domain which is closed. We add these rational points of the boundary. That's the idea. So definition, a rational polyhedral cone polyhedral cone in our vector space is the convex hull is let me how to say is a closed convex cone which is generated by finitely many integral classes. So that means by integral I mean in the lattice. So that's a rational polyhedral cone. And now the statement so theorem so this is it's not a hard theorem given a lot of work of other people and some previous work of us. It's also due to Stern in Kota case, and also due to Amerik and Verbitsky independently.
Actually, we have a slightly different version.
I know,
I'm not sure if it's quite the same. I have not checked it.
Okay. These are details. Assume the. Oh, are you saying that I should be wearing?
No, I think Morrison stated both versions and told that they are equivalent.
Okay.
But they're considered equivalent since then.
Okay. All right. So ours is very simple. So assume the boundedness conjecture. Oh, by the way, the description of the ample cone given for modularized spaces here was worked actually independently by Yoshioka for abelian surfaces. So Yoshioka did it. And you get again the boundedness for modular spaces of sheaves on abelian surfaces, and using you can prove it also for the deformations using the techniques of Hassett and of Mugabe. All right, so basically for all examples except the two special examples of O'Grady, these are not. For the two sequences we know the boundedness conjecture. All right, so assume the boundedness conjecture for X. So it's actually for the birational class of X. And then there exists, and I'll describe it, there exists a rational polyhedral cone, rational polyhedral cone D for for Dirichlet maybe, be inside this net plus, which is the fundamental domain for the action of the automorphism group of X on the net. Certainly, automorphism map net classes to net classes, and it's easy to check that it preserves this partial closure. Okay,
So our notion is that automorphisms have finitely many orbits on the set of faces of the cone.
Okay.
So I'm not quite sure
It's okay. I know how to derive the hours from yours. Okay.
but do you know how to derive hours from your assignment?
Oh,
No, it's
I
not
think
good.
so.
It's not good. It's clear that in the domain we find the meaning.
So as another corollary or another statement, we actually put the corollary before the theorem, is that in each there are finitely many isomorphism classes, finitely many isomorphism classes of irreducible holomorphic symplectic manifolds in the birational class of X. That's also it's not immediately. Yes, the rational geometers we see immediately how it follows. We call it along the way. Okay, so I want to make another remark. That actually, so this is a positive answer to a conjecture of Kawamata and Morrison, which they state more generally for Calabi-House. But usually it's not stated in terms of this funny F plus. So I want to say how it's related to the standard way to state a conjecture.
And the corollary was not known before?
I don't know. Was it? I don't think so. But
If it was, it is certainly in your papers.
I didn't know it before, but anyway. If X is of K3n type, then this net plus is equal to the intersection of NF. This is closed. This is a closed cone. It's a closure of the cone. Intersect the non-closed effective cone. This is the cone generated by effective divisors. So not closed. And moreover, this is true in general. So not only. So let me explain why. What's the relationship? The interiors are clearly the same, and because the ample classes are effective, and the inclusion from here to here would follow if you knew that every isotropic NF class is effective, which is a conjecture. This was proven by me in the K3n type case when I studied Lagrangian federations. So that's the other inclusion. And this inclusion, I'll let me explain to it. So the idea is very simple, and I understood it only yesterday. So that lambda be NF. There is a remark in our paper where it follows from Buxon's divisorial Zariski decomposition. Actually, it's elementary. Here it is. So that means that lambda. So need to show that lambda is in NF plus X. Now it suffices to consider. We may assume, because otherwise it's easy, that lambda is isotropic, so it's on the boundary of the code. So, all right. So now it's NF isotropic and effective. So, and then we will show isotropic, NF, and effective. But the remark is that this obviously shows that lambda is a multiple of a rational class. I'll explain in a second why, but that would be that's all, because then it will follow that it's here. So in F plus. All right, why is that? Because lambda is equal to summation ci di, where this is some reduced and irreducible divisor prime, and this is positive and real up zero. So this is the effectivity. And now lambda intersect di is bigger than or equal to 0, since lambda is NF. This is a standard argument in surface theory, is NF. And lambda, lambda equals 0. And on the other hand, it's a sum of positive real numbers times non-negative numbers. So this implies that lambda d is equal to 0 di for all I. So lambda lambda belongs to the null space of the span of reals of the classes of the di's. Now lambda is not 0, so the null space is not 0, but this null space is at most one-dimensional, and this space is the null space of a rational pairing on a rational vector space, so it's a rational subspace. This is rational, one-dimensional. So lambda is a multiple of a rational class. Yeah, because by signature. This lattice has signature 1, rho minus 1. So, all right, so that's it. So that's sort of a more geometric description of this NF class. And this is usually this intersection is referred to. So we don't know this equality in general, and in general people call it NF X E for effect. And that's usually how the Kawamata-Morrison conjecture is created. I should not erase the field. Oh, and I wanted also to say, what is this D? So, okay, I'm done with this remark. Let's say. So, what is this D? So D is not canonical. Choose Y in the ample cone such that Y, the stabilizer of Y in the automorphism of X is this is imprecise, is trivial. It's not clear that the automorphism of X acts faithfully on H2. So I mean, it's the stabilizer equal to the kernel of the. So maybe I should say stabilizer is equal. So the kernel of the automorphism of X is not embedded in all of lambda. Yeah, it's okay. So I should actually work with the image. The image. So the stabilizer under G is triggered. All right. So let dy d be depend on y. It's equal to x in the nef. So I'm not assuming that it's in nef plus. This will be part of the statement. Such that the y comma x is less than or equal to y, just a second, y comma gx, yes. This is for all g in G, where G is defined here. So these are related to hyperbolic distances. And this says that x is closer to y than any of its translates. And this is called the Dirichlet domain. And the statement is that this D is rational polyhedral. And we'll get to it. But it relies on a long point of the tau. Okay, so now I want to draw a picture, because all these codes are rather confusing. So I want to work up an example of the statement in the case, very simple case of a K3.
Sorry.
Yeah.
I think I missed something. What is A?
Where is A?
Automorphisms of A.
Oh, yeah, X. I don't know why. Okay, thank you. All right, so let X be, so this is an example. Let X be a K3 surface, be an elliptic K3 surface. Oh, this is let me call it P. Elliptic K3 surface with two sections. E0 and E1 disjoint. Such that the Picard of X is equal to span of let me say F E0 E1. Where F is a class of a fiber, and the intersection matrix is then, as we said, so F E0 E1, F E0 E1. I'm writing it because there's a result of Mikulim that says that this lattice can be embedded in the K3 lattice, and that proves the existence of X, or if you construct it explicitly, 0, -2, -2, 1, 1. 1, 1, and we want them to be disjoint. Now, so we get, so our lambda R is three-dimensional, because the Picard is like 3. But it's hard to draw pictures, three-dimensional pictures. So we have in it the positive cone, but it's convenient to work in the hyperbolic model. So let's work in this modulo R plus. So then we are working, that's actually the hyperbolic plane. It's a model of the hyperbolic plane. And so I'll draw the picture, I guess, here. So we have on the boundary, we have the isotropic class F. And now we can look at the image, the walls, because orthogonal to this E0 and E1. So we have these walls. And by the way, there are infinitely many rational curves, right? Because there's a cyclic group of sections generated by this, if you consider the group action. So these are walls. And the Neff cone of X is described by this picture. These walls will accumulate, so that will be infinitely many walls. These are all translates of walls corresponding to EI curve. And also there is maybe let me call this E naught. Pair. This is pair, the wall. And this is the EI curve here somewhere. And also there is the involution multiplication by -1. It's an automorphism. So there is, I'll draw this as the fixed locus for the involution multiplication by -1. Okay, so this is the Neff cone, and now we are looking for a fundamental domain. And so the fundamental domain is not canonical, but it's natural to choose it like this. So this is D. So it's kind of too thin. I should have maybe I should take this one. This is a fundamental domain, and the translations remove it, and it appears infinitely many times. It accumulates at the boundary, and this is a picture of what's going on. We needed to add F because we want the fundamental domain to be closed, and one vertex is on the bound. Okay, so
sorry, a stupid question.
Yeah.
Why do you represent the orthogonals like these things rather than straight lines?
it's hyperbolic.
Yeah, but it's too bad.
In this case, there will be geodesics. It's a theorem of hyperbolic geometry. You have in free space, the curve is two-dimensionally modeled by R. You get one-dimensional by geodesics. So geodesics are basic. So that's why. It's yeah. I mean, I'm using with the hyperbolic plane model for this. So there's a hidden isometry.
So projectivation of a positive cone is in fact
okay, so how am I doing? So I have half an hour according to my calculus. All right, so this is I hope that the statement is clear. Okay, so the main ingredient in this story is Verbitsky's global Torellis theorem. And there are other ingredients, but this is the main. Okay, so we need to talk about parallel transport operator. So definition. Let x1 and x2 be irreducible holomorphic symplectic manifolds. Let's see. An isometry or an isomorphism F from between the second cohomologies is called a parallel transport operator. Or for short PTO, if you are in the United States, this is what do I mean by this? If there exists a family, so irreducible holomorphic symplectic manifolds have a lousy moduli space, non-Hausdorff, and you need to choose something. So it's better to say parallel transport without saying without referring to a universal family. So if there exists some family, pi. Oh, I wrote pi here. Oh, that's okay. Pi from some family over a base. Which may depend on F. And we need it to be smooth, proper. Fibers are also irreducible holomorphic symplectic manifold. Points. So let me just now draw the picture. So here's B. So we need points B1 and B2. And we have the map pi. So we have XB1 and XB2, the fibers. And we need isomorphism of X1 with this. That's all part of the data. And we need also a path, gamma, continuous path from B1 to B2. And then we have the local system. And so we want, so all these data should exist such that parallel transport along gamma in the local system. So induces F. So that's what it means for F to be parallel transport operator. So it's the obvious thing. Nothing is mysterious here. It's what you would call a parallel transport. I guess I need to erase this. All right. So and then, so in terms of this, we can. Examples. So there are two examples of important examples of parallel transport operator. One is if let's say F tilde from x1 to x2 is a birational map, and both are irreducible holomorphic symplectic manifold, then there is a natural map from H2 x1 to H2 x2z. It's induced by the graph of F tilde as a correspondence in x1 plus x2. And this map and F tilde is a parallel transport operator. This is a result of Hilbert's. And this follows from his theorem that birational means non-separated. So the point is that, in fact, you can find a family such that x1 and x2 are two fibers and it's non-separated. So you can go from this x1 over this point, x2 over this point. You can go back into the main region, and then go to x2 along even the same path, and you'll get a path gamma that gives you a parallel transport operator. And the second example is that if let E in X, if this X1 is equal to X2, we call the parallel transport operator a monodromy operator. So let E in X be prime divisor, reducible irreducible, prime divisor with a negative Beauville-Bogomolov-Fujiki degree, then consider the reflection from H2X to itself actually, a priori, I'll write it this way. A priori, it's only rational. Part of the statement is it's in fact integral. This sends a class lambda to lambda minus 2 lambda E over EE, the class of E. So this acts by minus 1 on E and by plus 1 on the orthogonal complement. And this is a monodromy operator. Monodromy operator. It's parallel transport operator from X to itself. That's a theorem of mine using work of Duell and Amikawa. Okay, so what's the global Torelli? So these are I'm going to now state the global Torelli theorem.
I mean, you're assuming that this map is maps H2XZ into H2XZ.
No, I'm saying it's a part of it's a monodromy operator. So in particular, it makes integral.
No, but I mean.
Yeah, I said that.
You take any divisor with negative.
And as a corollary of the fact that it's a monodromy operator, it could be integral. So you can make it. But it's a mono. So there is a theorem of Duell that is contracted on some rational model. You can contract it, and I prove that if you have a divisorial contraction, then there is a monodromy. It's related to the fact the theorem of Amikawa that the contracted one is singular, the plurality space of the singular one. There's a there's a cover, branch cover, which is the deformation space of the smooth one, and the monodromy will be the monodromy which is double counted. Okay, so the theorem, the Torelli theorem stated in the language of monodromy is the following. So let X and Y. See, because you need a lot. You want to show that a very strange cone, this net plus, has a fundamental domain which is a closed polyhedral cone. So you need a lot of symmetries to translate a closed polyhedral cone to sweep up the whole strange cone. So the symmetries come from Torelli. So Torelli is the main ingredient. So Verbitsky. So two statements. One is the weak. So let's first let X and Y be irreducible holomorphic symplectic manifolds. So one, X and Y are bimeromorphic if and only if there exists f from H2XZ to H2YZ, which is a parallel transport operator and an isomorphism of Hodge structure. So this is an analog of the weak Torelli theorem. You know, for K3 surfaces, the statement would be if x and y K3 surfaces, then there is a Hodge isometry, which there is an isometry which preserves the Hodge structure. So the Hodge structure we want to preserve again, but instead of saying an isometry, we are saying parallel transport operator. These are all isometries, but not all isometries are parallel transport. 2 is a strong Torelli theorem. So let f from h2x to h2y be a parallel transport operator and Hodge isomorphism. That exists, so the question is, when does it come from an isomorphism? Notice that I'm not saying it when it comes from a birational isomorphism. That would be next. But so there exists an isomorphism f from x to y such that the f, actually this should be f tilde, such that f tilde is f, such that the isometry is f, is this parallel transport operator, if and only if this parallel transport operator maps a Kahler class, Kahler class is good. Some Kahler class to a Kahler class. Of course, once you know it's isomorphism, that's every Kahler class. Okay, so we have a strong Torelli theorem. And now there is a question: what is the strong birational Torelli theorem? How do you characterize parallel transport operators, which are Hodge isometries, which are induced by a birational? Remember, this was the first example here. The birational maps induced parallel transport operators. So we are missing a cone. Here, the Kahler cone is familiar, but we need another cone in order to state the strong birational Torelli theorem. And this would be the movable cone. And I see that I'm running out of time, so actually I won't get to this theorem, but I'll state the movable cone, which I already talked here in 2011. So the Kawamata-Morrison movable cone theorem conjecture. So X is an irreducible holomorphic symplectic manifold, here projected throughout the rest of the talk. So a divisor definition, so a divisor D on X is a divisor class is movable if the base locus of the linear system, if you want code, so sometimes, I'll just say it this way, but sometimes you take a sufficiently high multiple speed, so that it's a code, has codimension 2, B of m equal to 2 in X. And then definition, the movable cone of X is the cone, it's not closed. The cone generated by movable divisor classes And okay, so we have its interior, and we have MB plus. Let's see. I don't want to lose this. But we are looking for a version of the birational, strong birational torelli. Okay, so first we need a theorem of Buxon. Alright, so this will plus Heubrecht. So what? How do we characterize the closure of the movable cone? This is equal to classes in the positive cone. Oh, yes. So I'm working. Yes, this is all in lambda r, which is the Picard tensor r. So this is a lambda r, such that lambda paired with the class of a this E is prime exceptional divisor. Maybe I'll say it in the definition of set, where E is prime means irreducible divisor, such that its self-intersection is negative. These are called prime exceptional divisors. The exceptionality is this inequality here. So this was formulated in this way by me, and but it's most of you want to.
From bar, I mean, that's
yeah.
open, so you are in C bar and maybe in C bar.
Oh. Yes, you're right. Yes.
Okay.
Yeah, afterwards I need some classes. Okay, so this is one thing, and then yeah, so the second statement, this is better. The interior, you just constrict inequality. And so let's what does this? This has a corollary. So definition. Remember that every such divisor E gives you a monodromy operator. I have 10 minutes. So so given such E, we have a reflection by E, which was stated to be a monodromy operator. So let W, this is in the isometry group of lambda, be the subgroup. Actually, let me say it in here, H2 XZ. The subgroup generated by this reflection RE, where E is prime exception. Then the statement is that the movable cone is a fundamental domain from 26. So corollary is the movable cone. Let me say this. Yeah, it's kind of this is, roughly is a fundamental domain. Maybe intersect C. Is a fundamental. So this is the closure in C. Fundamental domain. Let's correct now. A fundamental domain for the action of W on the positive pole. This is because this is a statement in the geometry of reflection groups on hyperbolic space. That this is a chamber for. Okay, so that's one thing. And now the theorem, the strong birational Torelli. Let x and y be projective. Well, irreducible holomorphic symplectic. Let's say projective. Although I put it for non-projective, irreducible holomorphic symplectic manifolds. F from H2 x to H2 y parallel transport operator, which is a Hodges, which is a Hodges morphism. Then F is induced by a birational map from X to Y if and only if the original F maps some movable class in the interior of the movable cone of X to such a class of Y. All right, so I'll finish in 6 minutes. Let me. I'm using all my 80 minutes. So what is the? So that this theorem has a question. So this theorem has a corollary. See. This, if you combine this theorem with where is it with this statement that it's a fundamental, I guess this is a corollary. So let's combine this with this. All right. So we get the following theorem. You can take all the monodromy operator from X to itself, from X to itself, that preserves, which are Hodge isomorphisms. And then this is a semi-direct product of the birational, the image of the birational in the isometry group. So this is inside the isometry group of, I'll talk about the full second cohomology. So a semi-direct product, this is a normal cell. Semi-direct product is value. So this is almost it's immediate from this. These are all parallel transport operators. They all preserve the Hodge structure. And you can translate via the Weyl group, so they will map a movable class to a movable class. And if it maps a movable class to a movable class, it comes from the birational. So you get this. And this is what we need. One needs in order to get the movable Kawamata-Morrison. So let's see. So I'll state this and I'll finish. So let's. So we can define, like F plus, we can define the movable, this to be the convex hull of the closure of the movable cone. This is in C. Let's see. closure of the movable cone. This is in not in C, in the vector space. Intersect the rational vector space. So it's the same as the version of the math plus, but for the movable. And then the theorem is that there exists a rational polyhedral cone I'll call it pi, in this version of the partial closure of the movable cone, which is a fundamental domain for the action of the group of birational on this version of the movable cone. So this is the last thing I want to state. I want to just say the reason, and then things. So why is it requires a proof, but the point is that using this result, this semi-like product, which is an analog for the K3, you have a complete dictionary between results for K3s and the net cone and ample cone, and results for irreducible holomorphic symplectic varieties and the movable cone. And exceptional divides, this W will be analogous. And so the proof goes through, and the crux of the proof is the following: these two results. So the point is that this is essentially a fundamental domain. So to find a fundamental domain for the action of the birational group on the movable cone is the same as finding a fundamental domain, the same fundamental domain for the action of this arithmetic group on the positive cone. And this action of arithmetic group on the positive cone and finding for them fundamental domains is sort of a well-established theory. So and Sterk in his theory used this theory, and his proof translate word by word. So now using this, you can intersect this fundamental domain with images of left cones of birational models and analyze what happened, and you get that the boundedness, this left cones has the secondary walls, and the boundedness result tells you that walls of left cones will subdivide this fundamental domain into finitely many subdomains, which are rational polyhedral also. This is where the boundedness is, a conjecture comes in. And then you use hyperbolic geometry to finish, to get the ample cone version. Sorry, I don't have time. Thank you very much.
Other questions, comments? I suppose that this also implies, I mean, your result implies that the group of birational automorphism modulo biregular is finite, right? Or not? Birational automorphism modulo the subgroup of biregular automorphism. But isn't the existence of
Yeah.
yes.
Yeah, it's essentially the same statement. Yes.
Yeah.
Finitely many.
But it's not
Finitely many as an optical class.
So it's
No, it's absolutely yes. It's cool.
yeah, no, it's not. Yeah, okay. It's
No,
a
no.
finite index. Okay, you're right.
What?
No, yeah,
It's the same statement as the other code. There are finitely many as optical classes.
And you need, you need this boundedness conjecture.
Yes, yes.
More questions? Thank you very much.
I apologize for using all my
But maybe it's better because now we have a reception in the cafeteria, and I'm
I
almost
said